Okay guys, this is part 19 and we are continuing our comprehensive controller design for a MIMO system or MIMO system that was a set of two masses and the spring and dampers. Remember, if you go to part 18 you're going to see that, that's right. So we did the design control for when we release two masses, that is 2 degree of freedom system. It was this system, that's right. See, it was here and we had a damper here, and this is M1, this is K1 and the C1. We had a spring between them as K2, remember from previous class, and this is M2, and we had a spring here, if I'm not wrong, right, and C2, that's right. Let me see the code that I developed to make sure that it was the same example. Yeah, here we go. So, and we designed the intention, because a MIMO system, MIMO or MIMO, multi-input, multi-output. You have two controllers, right? U1 and U2 that you as a control engineer, you have to design them as we did. And you have two outputs. Outputs are the X1 and the X2, that's right. So, but the only difference with the CISO system, the single input, single output system that we had the example of the inverted pendulum, was the B matrix in X dot is equal to AX plus BU is what? In N by M. M is the number of input. So here is 2, here gonna be 2. But this is the 2 degree of freedom, the fourth order, it's gonna be 4 by 2. Remember that we had? Look at here in the code, and refreshing your mind, this is your B. This is 4 rows and 2 columns, the B. Here we go. I'm talking about this, okay? And obviously A is 4 by 4, because you have 4 state variables. Here we go, we generated the code here for you, previous class. Now then we designed by state feedback control law what? The U1 and U2. And I released the system from some initial position 0.5 for the X1 and 0.8 for the second one, that's right. And if you, for refreshing your mind, this was and we want that when you release that by underdamped behavior. Why? Because by the Ackermann formula, remember I told you that Acker works for CISO system. In MATLAB, you have to use the place command instead of the Acker. So the J, the desirable poles eigenvalue of the system here is the pair of complex conjugate poles eigenvalues, meaning that you want to have, as design engineer, based on your boss requirement, you want to design underdamped systems, right? So here we go, and so that's why you get this. See, from 0.8 starting, mass 2. Here we go, and the 0.5 goes to 0 to the origin. This is when, as I taught you several times, this is when that we want to push our system to what? To the origin. But the problem is that you have to show to your boss, or for judgment of your designing proper and feasible control input to the system, because in your actuator, that can be DC motor, can be solenoid actuator, you have to make sure that the controller that you design, or control signal that you are sending to your actuator, works well, has no chattering, is feasible, is not saturated, and because it's damaging your actuator. So that's why you have to see that U1 and U2 in the output. If you remember in part 15 that I taught you in the YouTube, at the end of the day, as I told you, use the con command and plot this. Now I'm teaching how to do that. So here, first of all, always, as I told you, you have to say clear workspace, clear all the parameters, every one that you try to solve your ODE, and the close all means after you have seen this, close all the windows, okay? These are the things that I'm doing. You have to say counter, but you have to make it global parameter, global con means that after this, when you run con here at 0, it's gonna share with the other M files in the workspace. So you have to do the same here, global con. Okay, now you're gonna make a counter. Con is equal to con plus 1. What is doing? Look at here, guys. Here it says con is 0 for the first time, but after it goes to the OD goes to inside this. For each time step, it's gonna add 1 to the con. So this gonna be 1, 2, 3, 4, 5, 6, 7, 2 times the number of the times. So here, if you want to put plot this U1, you have to say U1F con means put each of this U1 inside this. Gonna be U1. Now you are making vector of the U1. You are making a vector of U1. And U2F con is U2. But you have to make this as also a global, because you want to call it at the other file. 1F U2F. That's right. The same, you have to move it them here. This is how we plot this. Now I'm gonna plot them. But I have a point. Bear with me. Don't think that we are done. 2, and now time what? Control input 1 UF and U2F, right? I'm saying U1 control input that you are sending to actuator that make this happen control wise, and U2. So what do you expect to see, guys? Let me first debug it. Oh, it sees that figure 2 comes up, but there's error signal. Why? Because it says, here we go, because it says vectors must be the same length, time and U1 F is not the same. To avoid this always, this is MIMO method I'm teaching you, okay? You have to say, okay, time of con, because the time step that you are saying with the amount of vector you are saying are the same. You're gonna say now, put the time that exactly is counting on here. This is the time, that's right, T. And now make this again as time. Why this shift doesn't work? Shift, time, that's right, global. Please do it at home to make sure that you roll with me. Okay. Now if instead of the total time from OD you say time, these are tricks in MATLAB, huh? This is one method of plotting this. Now if I run this time, oops, you're gonna see the control inputs. This is the blue is for the mass 1 that we release from 0.5, and here release from 0.8. So you have higher for second mass, and both control inputs, as I taught you, goes to 0. Because why? Because your masses goes to 0 finally. Let me write it down here because this is not clear. So say C X label time, that's right, time in second. What the hell is with this? And then shift, copy paste, and this is Y label. These are what? These are X. I'm saying capital X because we have two state variable in meter. Okay, and now you have to put this here, time, and now is U. U is Newton here, that's right, because these are the force, these are the translational. So if I run it again, see, these are the U, the control input that you are sending, force that you are sending to actuator to generate, that's right, and this is time, U1 and U2. This is a MIMO system, and these are the X. Now if I change, if I say, you know what, I don't want to have the underdamped system, I want to have desirable poles at -2, -1, -1.5, -1.5, and -1.7, means that only I have the real part with negative eigenvalues or the poles. So here we're gonna get, right? See, guys? Completely critically damped system. There's no oscillation. There's no overshoot. That's right. I taught you in undergraduate control and the vibration. That's right, even in this course. So there we go. See that the control inputs is very different from, because it's like that. Okay? You can make this, I don't know, to 5 seconds to have the better judgment. See? Yeah, it's more white, that's right. So you want to need to understand. So now you design a controller when one goes to the origin. So we are done with this phase, but not this problem yet. Okay. So in the previous class, including this class, okay, it's recording. So we release the masses from non-zero initial conditions and then release back to the origin. That's right. The origin is here. The origin is here. That's right. And we design a controller for it. So, but the problem is that now suppose that x1 at 0 is 0, x dot 1 at 0 is 0, means they are at the rest, at their zeros here, right? So x2 at 0 is 0, and the velocity of that, because they are state variables, right, is 0. They are at rest. And I want to design a controller that pushes x1 at time infinity, x1 at time infinity to R1, that is, I don't know, say 0.4, and x2 at infinity, just move it this way, okay, from the rest, non-zero desirable input. So, and x.2 as R2 as, I don't know, 0.3. So you have non-zero, as I taught you, remember? And when I was teaching this, I taught you that if you have non-zero, the control input, general case, is going to be minus, again, kx plus k1, first element of that, in R. Remember, general? You have in your notes. I taught you. When you have non-zero desirable set points, like what? Like, say, for another example, suppose that you want to have suppose that you have suppose you have the temperature of the room at 75 Fahrenheit, and the temperature of another room you have 80 Fahrenheit. That's right. Or for the robotic system that you want to have push the joints of the robot to 45 degree and 60 degree. So you have the MIMO system that you want to design a controller for them. Okay. So now we have to implement this controller. Okay. So let us try it. So first of all, I have to go to the MATLAB code. Okay, for MIMO system. So you're gonna say, okay, let's do that. So, so the K is K. Okay, suppose that you want to have critically damped, almost response still. Okay, response, and the K is K. Okay, so what you're gonna do, you have to modify your use. Look at here, I'm just copying these, then commenting this. I don't want to lose them. So your u gonna minus kx, because you know that k has two look at here again from the previous class. Maybe you forgot that. Okay, look at here. See, your K has 2 rows. The first row was for the mass 1, this row, and the second row is for mass 2. If you have 3 masses, you're gonna have 3 rows. If you have 4 masses, if you have 7 degree of freedom robotic arm in my lab that I do have, you have 7 rows of the Ks. And these 4s is because of your state variables. That's right. You have 4 state variables. Okay, and because of those 4 state variables, you have 4 desirable what? Desirable pose eigenvalues of the system. Okay, 1, 2, 3, 4. Right? Order of the system. So let me pause it. Okay, yeah, K is K. So now you have to modify your U based on whatever entity, minus Kx plus K1. So now you have to define your R's. I said R1, your desirable things that you want to follow is point, how much is it? Is 0.4. Is 0.4. And the R2 is 0.3. Here we go. Right? R2 is 0.3. So now U1 is minus Kx plus, now I said the first element of the K, that's right, first element of the K, as I taught you, go here to notes, I developed the code. In K, again, 1 and 1, the first row, first element. We will examine, bear with me, okay? 1 and 1 in, I don't know what happened for this, in R1. 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 And now the second gonna be K, right? K and 2 on 1. Second row as I showed, and the first element again. That's right. In R2. Now I modified my control input to what? To follow, I have to make it count, to follow non-zero reference or desirable, what the hell is this? Desirable input. Okay, desirable input to follow non-zero reference desirable input. Okay, the same is for this. The same as for this. So now you have new 1 and new 2. So now by having these, let me see if that the controller works. Okay, so here I said I'm putting from 0 and 0 because in the rest. Now I'm gonna design controller to push it to non-zero positions. This mass 1 and mass 2. Understand? So let me first try with you. Okay. It pushes the first one to, look at here guys, pushes the first one to this first one must be 0.4 and 0.3, that's right. Pushes the first one to how much? To 10 times of that, and it's -6. That's right. That's funny. That's right. So what's wrong with this, guys? See, you are huge numbers. What's wrong with this? I'm gonna pause it to give you time to think. Okay, guys. So what's wrong with this? Why, when you're running this, we don't get to what is that? To 0.4 for the mass 1 and 0.3 for the mass 2. Why we don't get there? Get here. Why we don't get there? One of them goes to 3 and -6. What's wrong with that? Any ideas? I'm just going to give you a hint. The hint is this. Guys, I taught you in part 15 or part 14 that this controller, change the color, U is minus kx plus kir, works for plant with non-zero reference input, but with integrator in with integrator in the plant. So what do you think? Guys? Do we have integrator in the plant, in the transfer function? On the other hand, look at here, guys. If this is the transfer function of this MIMO system, and if this is the transfer function, which is output over input of the system, if we have a controller here, do we have one S in whatever here is inside? Do we have integrator here in the plant? I want that you go and calculate x1 over u1 as homework, and the x2 over u2 as homework also, and see if we have an integrator in the plant for each mass. Okay, it's warming up. Hold on, I fixed this, guys. Okay, so after finding this, you will see that there is no integrator for each of them. And don't forget, when you are finding this, you have to apply the superposition principle, and you have to assume that there is no, if you want to calculate x1 over u1, you want to assume that there is no u2. When you are using x2 over u2, you have to assume there is no u1. That's right. And you will see, please do it at homework, and there is no integrator. So what's the solution of this, guys? Right, it is holding. Okay, so what is the solution? Solution is, I want that you try as homework. Okay, first try it. The solution is that after knowing that there is no integrator, the solution is this control that I taught you, kx plus ki zeta. But the tricky point for the MIMO system is this. Please go and do at home and develop the code that you have it, and remember that the zeta dot, as I told you, was r minus y. Y is cx. That's right. Please do it. This is very interesting for the MIMO system. Okay. So what you're gonna do? You're gonna have a hat, as I told you previously, that you're gonna have a0 minus c0, but your a is 4x4 matrix and the c is 2x4 matrix. That's right, remember? So this is gonna be 6x6, and the b hat must be how much? B and 0 must be, because this is 6, gonna be 6x2. So you're gonna have 2 zeros. On the other hand, your b gonna be your old b 0 0. Make your 6 0 0. Remember that, because if you look at the code, and your c, you can make it as because now with this you're gonna have 1 0 0 0, 0 0 0 0 1 0 0 0 to be consistent with this is 2 by 6. Everything is based on 6. Okay, and then you can design this. I solved this for the pendulum problem. I want that you go and have hard time and do as homework for this system. Understand what I'm talking about? Okay, now after the controller, I have the solution, guys. Don't think that I don't have. I have the solution. Oh, that was too fast, huh? But try it, okay? Try it at home. Or I can try it here. Don't worry. It's just like this. But you can do it at home. So your A is 6 by 6. Look at here. It's 6 by 6. There is A 0 0 added here. A previous 0 0 added here. A 0 0 added here. A 0 0 added here. A no, this is minus C. This is minus C. 0 0 added here. Minus C 0 0 added here. B is the old B that we had, and now 2 zeros to make it consistent with that. So let me do that. But because you increase the order of the system, because you have two systems, you have two zetas. These are zeta dot 1. Look at here, guys. You have zeta dot 1 and zeta dot 2. And say R1 is 0.4, R2 is 0.3, right? And so zeta dot is R1 minus Y that is for 1, R2 minus Y2. So, and you see that your J gonna be changed because you have no 6 order system. You have 2 zeta added. So minus 1 minus 1, you have 6 desired angle values of the poles. That's right. You have to be consistent. And your C is the previous C, previous C, and 0 0. Previous C 0 0. Then now you have K. That's right. So let me put pause here. In the previous case, that when we want to go to the origin, we had 2 by 4 K. That's right. Now we're gonna have how many Ks? 2 by 6. Look at here. I'm running for you, guys. Here we go. See? Okay. See? Now our K is 2 by 6. This is for mass 1. This is for mass 2. Why? Because we have zeta for this one and zeta for this one. That's right. We have 1 zeta here added, 1 zeta added here. That's right. Understand? So we increase the order of the system because our controller has no. We are adding the virtual integrator to the system. What the hell is that? Okay, understand? So we have, look at here, we have, now we have, I'm writing here, we have 2 by 6 gain matrix. Why? Because we added 2 zetas as there is no integrator, and hence we add integrator, say virtual to the plants. Okay, please writing your code to make sure that you have the comments. Understand? Moving pause. So we have K, and these are our R1 and R2. Now you have to modify your U. See, U is minus K, but your new X is 6 state variables. That's right. M1 position of mass 1, velocity of mass 1. This is zeta. M3 is zeta. This is zeta 1. M4 position of mass 2, velocity of mass 2. This is zeta 2. That's right. And now K in zeta. That's right. Look at here. K in zeta. for each of them. Zeta 1, y1, u2 gonna be plus k2 zeta 2. That's right. So this is zeta. Zeta is m3, m6. How you know it? I just generated here. dm3 is r1 minus y. Okay, but y is cx again. Your c is x again. So your y gonna be how much? Gonna be 2 by 1 vector. 2 by 1 vector. So its first row is for first mass, and its second row, what is row, is for second mass. That's right. Row is like that. Understand? Right? So you have now 6 state variables. Here I modify to 6 state variables. Understand? So, but we have to be careful about the gain. Gain is third element, because the zeta is a third element. This is 6th element, because this is 6, 2, 6. So after doing this, okay, now you have modified everything. Let me close this. You have modified everything. So if I do that, here we go. Okay, it's coming up. Okay, this is your x. M1 want to go to 0.4 meter. This one to go to how much? 0.3 meter. But it still isn't transient, so it takes more time. That's right. So you have to increase the time. So you see that these are the U's, control inputs that goes to actuators. So you have to increase the time. Say, I have to say to 50 seconds. Why? Because I said my system wants to be critically damped system. Critically damped system is much slower than over damped system. I want that you type this. I won't share it in Blackboard because it makes lazy. I want that you do it by your hand, okay? For after graduation, okay? Type in on the MATLAB. I'm sorry. So we'll see. Let us see what's happening. It's coming up. Okay, I think that we are close. Yeah, it's still, see, this first converges to 0.4 much faster than the second. Second is asleep, has time. So let me increase to. That's why designing that critically damped system, as I was teaching in the vibration, the graduate control, critically damped system takes much longer time to reach to. That's right. So let's see, for 100 seconds it takes for this kind of system. And the mass was how many? Mass was 1 kilogram, 1.1 kilogram. That's right. Almost there. Okay, these are the U's. See, control commands. Yeah, almost there. 0.3. So, but if you want to reach that much faster, what's the solution? You are a control engineer. Just make it, guys. A pair of complex conjugate poles. Minus 1, or was it minus 1 plus I, over 0.5. This is minus 0.5 plus I, and this is minus 0.5 minus I, and minus 1.7. Obviously, real parts must be negative to make this stable systems, right? I told you. See, minus plus minus, minus plus minus. So let us now try this for 20 seconds compared to that. See, 0.4 and 0.3. Maybe the problem nature is too much. Let us see 100. No, this is under damp response, right? Because you have oscillation in transient response. Yeah, obviously at 60 seconds, see? In the previous case for the critical damp system, we never reached at the, even at the 100 second. But here almost in 60 seconds we reached it. Even at our system 100, and these are the control commands. Here we go. See? 60 seconds. We have overshoot. You can handle it by tuning the desirable pose eigenvalues, but we reached that values. Now we design controller for a MIMO system. I want again you type these one by one and understand what I have done, especially this part. Why I selected third and sixth? Because these are the attributes to those details. Understand what I'm talking about? Okay. And obviously here, because I added two state variables, zeta 1, zeta 2, you have 6 initial values, 0, 0, 0, 0, 0. And okay, so that's it. Now let's go to the next topic, which is designing observer. Designing observer. This week and next week I'm gonna devote to designing observer. So state observer. Okay. In the pole placement, we assumed that all states means state variables, all state variables are available for feedback. Remember that it was the U minus KX state feedback. But in reality, all of them are not measurable, and hence we need to estimate them. Observation means we are estimating, because suppose the sensor has malfunction, or we are estimating the state level, or you have no sensor to measure them, even sometimes proper sensor, so you have to estimate. Observability means that you are estimating the state values. So estimation of unknown state or unmeasurable state variables, like as the temperature. Suppose that your temperature sensor in your home has noise right? And you cannot measure it correctly, so you have to estimate that for the controlling for having the state feedback. So state variables are called observation. If the system observes all state variables, it is called full order observer. Full order observer. If you can observe or estimate all state variables, it's a full order observer. Okay. So an observer that estimates fewer than n for nth order system n state variable, it's named reduced order observer. Reduced order, so full order, reduced order observer. Okay, so we measure state variables based on the measurements of the output and control variables in theory, but when you go to practice, it's gonna be different story. I'm gonna teach you the next class.